Okay, we're continuing with more counting example problems. This is part 5. And so at this point, the level of difficulty of these problems is as hard as they can get. Parts 1 and parts 2 were a little bit easier, but once we got into part 3 and part 4, then all possible scenarios could take place with a certain problem. Subtracting out answers, applying the Venn diagrams, mixtures of different counting methods within the problems, etc. How many different strings of length 10 or more can be made from the letters in abracadabra? So 10 or more. All right, so we're going to need to use the sum rule here, add up different outcomes. But notice for this example how, and this is the case with a lot of examples where you just use like the OR criteria. From the perspective of the Venn diagram, none of the outcomes we're going to add are overlapping. So, for example, the outcomes of 10 length strings, character strings, and 11 character strings, those don't overlap. There's no 10 character strings that are also 11 character strings and vice versa. So, okay, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 characters. Let's just start by calculating the number of words that come from the 11 character string words, because it's 10 or more. Okay, now we've got 1, 2, 3, 4, 5 A's. We've got 2 B's, 2 R's, and a C and a D. So 5, 6, 7, 8, 9, 10, 11. So, okay, we can divide this by, and there we go. There's the total 11 character strings we could make from abracadabra. All right, now, what about the 10 character strings? Well, we're going to need to break this up into different events. Like if you had a whole Venn diagram for 10 character strings, I mean, we can do this for, so here's all of the 11 character strings. This is the entire system. Here's all the 10 character strings. There's no overlap, right? System, 11 character. I guess this would be bigger, right? Doesn't matter, but 11 character, 10 character. But within here, we want to say, okay, what if we picked, so we can omit one of these letters for the 10 character string, right? We can omit an A, a B, an R, a C, or a D. So, okay, if we omit, here's if we omit an A, here's if we omit a B, C, D, R, okay? So omit A, etc. But are these overlapping? If you're not sure, then go ahead and assume they're overlapping and write it all out, the whole union formula. But we can just think about this. Is there any, for these strings here, right? Order matters. Order matters. So for these strings, if we omit an A, then we're going to have 4 A's, 2 B's, 2 R's, a C, and a D. Well, none of those are going to overlap with when we omit a B, because for all of these, we're going to have 5 A's. None of these we're going to have 5 A's. So all of these are going to be different. There's no overlap. You've got distinct letters in all of them. In fact, even with combinations, they shouldn't overlap, I don't believe. Maybe not there, but I'm thinking that just off the top of my head, they wouldn't overlap because you're going to still have a distinct group of letters in each of these. And that's kind of how combinations works. It doesn't count the reorganizing of the same distinct group, but all of these groups are going to be distinct. So, but regardless, we're doing permutations anyway, so there's definitely no overlap. Okay, so let's start by, okay, if we omitted an A, then the result is we've got 10 factorial, 10 characters over 4 factorial times 2 factorial times 2 factorial. So, okay, 11 factorial over, all right, now we're adding 4. Okay. Now, what if we omitted a b? Well, then we would have 10 factorial over just 2 factorial. Oh, no, but then the 5 factorial for the a's. Okay, but that's going to be the exact same thing for if we omit the r, right? So we can just multiply this by 2, and these cancel, so you've got 10 factorial over 5 factorial. Okay. Now, what if we omit a c? Well, then we've got 10 factorial over 5 factorial, 2 factorial, 2 factorial, but that's going to be the same as if we omit the d. So multiply by 2. So we've got and that is it. There's the total count. Suppose you planned on giving 15 gold stars to some of the 23 star students in your class. Each student can receive at most 1 star. How many ways can you do this? Okay, so it looks like this we can just use the combinations with repetition because the students are unique, right? They're different. The stars aren't, but so let's see. We could think about the bins here could be each student, right? Each student, and then we've got, or no, maybe we're choosing from the students to apply to the stars. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And now we're choosing from the students. So how would that work? Yeah, this is just combinations because the order doesn't matter, right? It's just the snapshots of each distinct group of students. So this is just going to be 23, choose 15. If a coin is flipped 8 times, how many possibilities contain at least 3 heads? So, okay, a coin is flipped 8 times. So here we're just breaking it down into ors. Now, but what we want to do, though, is it's going to be easier if we start with the total number of outcomes and subtract out what we don't need. So this is a permutation with repetition. No, it's combination with repetition. Let's see. We can choose a head or a tail, and we can repeat, but does the order matter? If we do, no, it doesn't. So it's combinations with repetition, and if all possibilities are okay, so the total system outcomes is we're choosing from 2 for 8 slots. 8 plus 2 is 10, minus 1 is 9. 9, choose 8. So that's the system, right? That's all the outcomes in the system, and we're wanting to subtract out the possibilities that contain 2 or less heads. So do we have anything overlapping here? So the possibilities that contain no heads, possibilities that contain 1 head, possibilities that contain 2 heads. If you're not sure, then just assume they're overlapping and then go from there. But so we can think about this, that no, if there's no outcomes, if you have just 1 head, there's no outcomes that also have 2 heads at the same time. So there's no overlap here. All right, so if it's all tails, that's just 1. Okay, what if it's 1 head and the rest tails? Well, okay, no. 9. Okay, 1 head and the rest tails. That's just going to be, we're choosing from 2 for 7 slots. So, or wait, no. Is that right? You have one, okay. All tails, one outcome. If you've got one head and the rest tails, well, okay, that might not be what they're saying here. That's just one outcome as well. The total outcomes for this entire system is 9 choose 8 is 9, right? You could have all heads, tails. So you could have 8 heads, 0 tails, 7 1, 6 2, 5 3, 4, or no. Yeah, 4 4, 3 5, 2 6, 1 7, 0 8. 1 2 3 4 5 6 7 8 9. But that can't be what they're talking about. Or maybe it is. Okay, well, if it is, then the answer is there's 9 outcomes. The answer is there's going to be one that contains no heads, one that contains one head, one that contains 2 heads. So the answer in that case is 6. If they're saying that order matters, then it's, okay, this is permutations with repetition. So it's 2 to the 8th is the entire system. And then we're saying, okay, if there's one head, or no, let's start with, if it's all tails, that still is just 1. Now, if it's a head and all tails, then you could just put that head at any of the different slots. That's going to be 8. If it's 2 heads and all tails, then that's just, okay, we do 8 factorial over 2 factorial, 6 factorial. So that's 8 times 7 over 2. That's 28. So 2 to the 8th minus 37. Is that right? Yeah. In the real estate ads, there are 100 homes for sale with garages and 42 with swimming pools. If there are no homes with both a garage and a swimming pool, how many total homes are for sale? Okay, so here we can just use the Venn diagram. So we've got, let's see. We've got 100 homes for sale with garages and 42 with swimming pools. No homes with both a garage and a swimming pool. So, okay, let's see. The system is all homes for sale. And it looks like we've got these 2 scenarios here. We've got swimming pool, garage. So all the homes that have swimming pools, all the homes that have garages. Maybe that's how we should model this. And there's 100 homes that have both. And there are no homes. What? Oh, okay. No. There's 100 homes for sale with garages, 42 with swimming pools, and no homes with both a garage and a swimming pool, so there's no overlap. Garage, swimming pool, 42, 100. How many total homes are for sale? 142. Okay. If there are 29 with both a garage and a swimming pool, so, okay, let's come back. So now we do have some overlap in this case. So swimming pool, garage, there are 29 with both a garage and a swimming pool. So, but what's the criteria though? Are we still saying that there's 100? Yeah, I guess they're saying it's 100 with a swimming pool or with a garage and 42 with a swimming pool. And now they've just changed it to where instead of having no homes with both a garage and a swimming pool, there's 29. So how many total homes are for sale? Well, okay, but this is the whole system as well. For the first problem, I drew 2 circles, but that's actually the whole system. So we can like erase this. This is the system. And I could have done that for the previous problem. There's nothing outside of our system in this case. They're saying that these are all of the homes. So again, this is the system. So, okay, if we call this, I'll do SG. So we're looking for S union G, the number of elements, right? That's all of this with no duplicates. So we know that's going to be, and then minus, right? So that's 42 plus 100 minus 29. So 42 plus 100, 113. How many positive integers not exceeding 1,000 are divisible by 7 or 11? Okay, so in order to solve this problem, you do need to know a little trick that probably a lot of you watching this video aren't familiar with. Well, it's not a trick, but it's just, so, okay, the whole point of this problem is to think about when you might need to use Venn diagrams. So what we're looking for is if set A is all of the numbers that from 1 to 1,000 that are divisible by 7, and set B are all the numbers, the integers from 1 to 1,000 that are divisible by 11, then we're looking for the number of elements in A union B, right? Because this doesn't include duplicates. But the only issue is that we don't know about any overlap in this case. It seems like there would be overlap. Maybe there's not. But are there, here's all of the integers between 1 and 1,000 that are divisible by 7. Here's the ones that are divisible by 11. But is there a mixture where you have some numbers that are divisible by both? But here in the entire system, here's all the numbers that outside of these sets that aren't divisible between 1 and 1,000, all the integers that aren't divisible by 7 or 11, right? So if we wanted to solve for that, we could as well. Just subtract this out. But, okay, but we know that this is going to be equal to all the elements in set A, all of the elements in set B, minus, right? So, we can start by how many integers from 1 to 1,000 are divisible by 7. Well, we can just we can say take the floor function and input 1,000 divided by 7, right? So floor function would be 142. And why does this make sense? Because if 1,000 divided by 7, you're doing 7, 14, 21, 28. And if you keep adding 7 all the way to 142 times, you're going to get all the way to 994, right? That's 994 is 7 plus 7 plus 7 plus 7. There's 142, but you can't add another 7. So, okay, so we have 142 here. Now with B, do the same thing. It's the floor function of 1,000 divided by 11. So 90. Okay, now, we could assume that the sets overlapped. It doesn't matter because if they actually don't overlap, then once we analyze it, then we'll just put 0 here. But okay, do they overlap? We need to subtract out all the numbers that we kind of double counted because they were both divisible by 7 and 11. All the integers from 1 to 1,000. And so this is the trick I'm talking about. If you don't know this property, then you won't be able to figure this out. But the whole point of this problem is just to get you thinking about using these Venn diagrams. But what we can do is, because 7 and 11 are relatively prime, which means that they don't share any common factors. So like even 8 and 15, these aren't prime in and of themselves, but you call they're relatively prime because you've got 4 times 2, 2 times 2 times 2, and here you got 5 times 3. They don't share any factors, right? And so what that means is that it just allows you to say that all of the numbers, the integers from 1 to 1,000 that are divisible by both 7 and 11, you just do this. Since these two are relatively prime. That's the trick. So, okay. 1,000 divided by 77, and that's 12. So, okay. And that is the answer. So, 142 plus 90 minus 12 is 220. How many permutations of the letters A, B, C, D, E, F, G contain the string ABC in that order? All right, so what we want to do here is we can think about how if we say this big capital A is the string ABC, then in that case what we've got is this big capital A, B, C, D, E, F, G, H. And now we can just calculate the total number of ways to arrange these letters, right? Because you can just put this capital A anywhere because it's just A, B, C in that order. So 1, 2, 3, 4, 5, 6, 7, 8. But, okay, no, hold on. I did that. Yeah, I got to take out the B and the C. So there's the A, B, C. Then we're left with D, E, F, G, H. So now you can just put this big capital A anywhere you want, right? So, okay, what's the total number of ways you can arrange these letters? That's 6 factorial. There's 1, 2, 3, 4, 5, 6. And that's it. There's no duplicates. So that's it. Professor Brem has just completed writing the final exam. The exam has 12 questions for a total of 200 points. How many ways can Professor Brem assign points to the 12 questions if each question must be at least 10 points, but no more than 25 points? And all point values are a multiple of 5. So we can think about this as a balls and bins problem, which is usually it's combinations with repetition. And we can also model that this way. So it's like you've got this x1 plus x2. Okay. Okay, now these add to 200. Each question, the point values assigned to these 12 questions adds to 200, right? And so now, but they're all integers. These are all integers, positive integers. This is another way to look at the bins and balls problem because the order of the bins doesn't matter. It's the same bins, right? You could flip the X4 and the X5. It doesn't matter. And you've got all these balls, which are these points, these 200 points you can put in any of the bins. And that's where we use the combinations with repetition. But here we've got some restrictions. So there's a lower limit, that's pretty easy to deal with, where each question must have at least 10 points in it. And then we also have the point values are a multiple of 5. So what we can do with that then, with the point value restriction, is that we can think about, we've got this bag of tokens here that are worth, okay, it'd just be a circle, that are worth 5 apiece. Okay. This bag of tokens. And so we can put a token in each slot, and now the total number of tokens is going to be, so 200 divided by 5 is 40. So we've got a total of 40 tokens, but each bin here needs to have at least 2 tokens, 10 points. And so the lower limits are easy to deal with because all we have to do is just say that, okay, that means each bin has to have at least 2 tokens. So that's 24 total tokens. 40 minus 24 is 16. So we can just change this to 16. That's it. And we've got these 16 of these 5. They're worth these tokens to distribute. And remember, you might be saying, well, why does it work that way? How can we just change this to 16 and solve it? Because all we're solving for is the total number of combinations, the total number of ways the professor can do this. So if we solve also what's changed now, okay, yeah, we can, yeah, I didn't specify that clear enough. So this is now 16, and we can solve this same problem with no lower limit now. Now, any of these bins, we want to distribute these 16 tokens to these 12 bins, but the bins are allowed to have no tokens. If you could put all 16 tokens in bin 1 if you want. That's what we're wanting to solve. Well, but if there's any upper restrictions, we have to consider those. But we can just eliminate the lower restrictions. So yeah, we're not going to be able to do that because we can't put 16 tokens in bin 1 because you can't have more than there's an upper limit. But the reason why that worked is this. Because we're just going to solve for the total number of outcomes. And let's say we get 500 outcomes. That's our final answer. So you can think about each one of those outcomes has like a picture associated with it. And the picture is going to be, you're going to have some of the questions are worth no points. Some of the questions are worth this points, etc. Well, to get all we have to do is update those 500 pictures by just putting an extra 2 tokens in each bin. That's it. It's the same number of outcomes. You just come back in the end and say, okay, put 2 tokens into each bin, right? Because we're just counting the outcomes. Okay, but however, we can't just solve this and allow for X1 to have all 16 tokens because we also have an upper limit, which is a little more tricky to deal with, but we know how to deal with this. What we're going to do is we're going to start by solving for the case where you are allowed to have, there's no upper limit. So what's that going to be? Well, it should just be the combinations with repetition. So we're going to have the 16 tokens laid out, and we're going to be choosing from the 12 bins with repetition. So you could choose all 16 tokens you could assign to 2. To X2. You could assign, again, all 16 tokens to X2 if you wanted, right? Now, let's make sure this makes sense, though. So, yeah, because, yeah, it is combinations, so order doesn't matter, but we do want to have distinct bins, though. Like, we are counting, if you assigned this token here to bin, let's say it's bin C, and you assigned this token to D, then you don't care if they reorder themselves. If they reorder, that doesn't matter. But you do want to have labels on the bins, A, B, C, D, E, F, G, all the way to 12, because you want to know, okay, like you want to know if I've got 5 tokens in bin, it would be, if I've got 2 tokens in bin 12 and 1 in bin 11, but I flip that, I put 2 in bin 11 and 1 in bin 12, I want to count, those are different. So, okay, yeah, this is fine. So all we have to do is say combinations with repetition. We're choosing from a group of 12, and there's 16 spots. So combinations with repetition, we've got 16 plus 12 is 28 minus 1 is 27. Choose 16. So there we go. That's the big number. But now we need to subtract out the cases where you have any one of the bins has, in this case, it would be what? So the limits have been updated to, you can have 0 tokens in a bin, but you can't have more than 4 tokens in a bin, because you can't go past 15 now. So the any of these x's can't be, they're all less than or equal to 3. So we want to solve for the cases where any one of these bins has 4 or more tokens. So we just do the whole, we're looking for, if this has been A, B, C, D, E, F, G, then we're looking for the number of elements in A, union B, union C, and then all the way to the 12th letter of the alphabet. All right, now, like we've done before, I'm not going to go through explain every detail of what we're doing here. I've explained this in previous examples, but this is not going to be as cumbersome. It's not going to take as long as it seems, because once we get to a certain point, you can't have, it's not possible to have 4 tokens in 4 or more bins, right? So, okay. We start off with just like how many are in A, B, C, right? So this is going to be, the total number here is going to be 12, choose 1. That's the total number of like, there's 12 letters, right? There's 12 bins. Okay, we're multiplying that by, so what is the total number in A intersection B? Let's start with A intersection B. So the total number, yeah, so if you have A has, bin 1 has 4 more tokens and bin 2 has 4 more tokens, now you've got 8 of the 16 slots taken up. You're left with 8. So it's 8 slots. You're choosing from 12 bins. So that's 20, that's 19, choose 8. So all we need to do is just take multiply 12 by 19, choose 8, because all of the intersections are going to be the same. Or wait, no, hold up. Yeah, I did that wrong. So no, this is, so we yeah, what am I doing? So we subtract the A intersection B, A intersections, yeah, wait. So this is going to be 12, choose 2, then 19, choose 8. Because there's the different pairings, you take 12, choose 2, right? A intersection B, A intersection C, A intersection D. It's 12, choose 2, because the order doesn't matter. We don't count B intersection A. It's all the same. So it's just it's 12 buckets, choose 2. And then I just counted one of the intersections, A intersection B, but it's going to be the same for all the intersections. It's the same idea. So it's 12 choose 2 times 19 choose 8. But here, 12 choose 1 times how many elements are in just A. If bin 1 contains 4 or more tokens, then what's the total count there? Well, okay, you've got 4 slots taken up, so there's 12 slots left. So it's 12. Choose 12, combinations with repetition. So it's 23, choose 12. So this is 23, choose 12. Okay, now we add all of the triples. So A intersection B intersection C, A intersection C intersection D. How many of those are there? That's 12, choose 3. That's all the different intersections you could have. And you're multiplying that by, so what is like A intersection B intersection C? That's when you've got 3 of the bins have at least 4 tokens. So that gives, that's 12 slots are taken up. So you've got 4 slots left. You're choosing from 12 bins. 12 plus 4 is 16. So 15, choose 4. Okay. Now, finally, we subtract. There's going to be 12, choose 4 of these, of the intersection of 4 sets, like A intersection B intersection C intersection D. Again, if you're confused, you need to go back to the previous example problem videos. I explained this slowly in other videos. So, okay. If you've got 4 bins that contain at least 4 tokens, then all the slots are taken up. So you're doing 12, choose 0. So that's 11, choose 0, which is just going to be what? That's just 1, right? And that's it. That's it. That's the total count. That's the total number of outcomes from 27 choose 16 to where at least one of these bins contains 4 or more tokens. And so all we need to do is just subtract 27 choose 16 from this. And that's the answer to the question, the main question here, because you're doing, so in terms of, if I stop talking about tokens, and then just the way this is set up, this is the total number of ways the professor can distribute. So it would be 200 minus 120. So, okay, if you have 12 questions for a total of 80 points, and the point values of each question have to be multiples of 5, but each question can be worth no more than 15 points, then that's the total count. But the idea is all we do, we take each of those snapshots, and we just say, okay, take each one of those and just scale it up by 10. So if you had a question that was worth, that you assigned 0, right? Let's say for one of those outcomes, question 2 was assigned, it was worth no points. Well, then you just change that to it's worth 10 points. If you had question you go through every snapshot and you go to all the questions and you just add their worth, the worth of that question, to add 10 points to it. And so for each snapshot, you're going to see all the questions are going to be worth no less than 10 points, no more than 25 points, and they're all going to add to 200 in that case, because you added 10 to each of the questions. That's add 120 to 80. Now the whole test is worth 200. And you just do that with all of the snapshots. And so, but it's still the same number of outcomes. How many different poker hands are possible using a standard deck of 52 cards? Okay, so you've got 5 cards. There's 52 to pick from, but we're not repeating anything. And order doesn't matter. So this is just going to be 52, choose 5. How many different ways can I choose 47 of the 52 cards in a standard deck of cards? So this I guess order must matter, or maybe not. Yeah, if order matters, it's going to be 52P47. If order doesn't matter, it's going to be 52C47. In how many ways can 14 people leave the Christmas party with a different gift than what they brought for the white elephant exchange? So this is that derangement idea here. You have people that they're coming in with a gift, their own gift, right? So now we want to calculate the total number of outcomes that completely scrambles that initial order to where there's no pairing that's on what it was originally associated with. Okay, and this is that principle of inclusion-exclusion again, what we just did a couple of problems ago with just you're not allowed to. So yeah, let's go through this. You've got, we come in A, B, C, D, E, F, G, H, all the way to 14. Okay, if you take 14 factorial, then that's all of the possible ways that, here's gift A and here's person A, gift B and person B, right? 14 factorial is all the possible ways that you can have a gift associated with a person, including if a person has their own gift, right? It includes this where every single person has their own gift, but it includes where just person A has their own gift and no one else does, etc. we're trying to subtract out all scenarios where any person has their own gift. We want to subtract that out from 14 factorial. Okay, and we use that whole Venn diagram idea where we're thinking about we have these 14 sets where each set is the number of outcomes where like person A has their own gift. As long as person A has their own gift, that's an outcome of that set. Then another set is where person B has their own gift. We're trying to get the union of those 14 sets. So it's all of those outcomes, but the duplicates are removed, right? What we're looking for is assuming that set A, set B, set C are only the outcomes where person A has their own, hats, their own gifts, right? And set B is the outcomes where no matter what it is, as long as person B has their own gift. Okay, so we just start with, I'm not going to explain the details of what I'm doing here, but because I've done that, I've explained that previously, but okay, we start with 14, choose one, right? Then, because we've got these 14 sets, then okay, in one of these sets, it's going to be, so if that, what's one of these sets going to look like? So here it's going to be, so if person A has their own gift, they're set here. What we're left with is 13 factorial. Right? Person A has their own gift, and then you can rearrange these however you want. Okay, so now then we want to subtract out the different intersection pairings. So that's going to be 14, choose two of those, and then, okay, if both, yeah, and so it's 13 factorial, but we just multiply it by 14 because it's the same idea. If D has their own gift, well, then it's just 13 factorial again. And so, okay, now 14, choose two of the pairings. Now, okay, what is like A intersection B? So if A and B both have their own gift, then it should just be 12 factorial. The number of outcomes where both A and B have their own gift, these are fixed. Then you just rearrange these as much as possible. But we don't have to think about, okay, what if these two switch spots? Well, then no, then they wouldn't have their own gift. They're fixed. Okay, so then we can see that the pattern here is going to be 14, choose 3 times 11 factorial. And is there any stopping point here? Because there's usually a point where the intersections just go to 0. But I guess in this case, that's never going to happen. Because you can have the intersections can go all the way. You could have A intersection B intersection D intersection C intersection D E F, because they could all have their own gifts. So yeah, it's just you do 14 and then okay, and I think we do need to go to here. Because this is when you've got, let's see, what is this? This is, oh wait, what did I do here? Hold on. 5, 6, 7, 8, and then this is, okay, wait up. So 8, 9, 10, 11, 12, 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Then, all right. Okay, then I did 13, 12, 11, 10, 9, and then this should be 8, 7, 6, 5, 4, 3, 2, 1, 0. So 10 factorial, 9, 8, 7, 6, 5, 4, 3, oh, come on. 13, 12, 11, 10, 9. 8, 7, 6. I'm running out of energy. I gotta take a break. 6, 5, 4, 3, 2, 1, 0. And do we need this? This last one should be necessary because, yeah, it's just 1. 0 factorial is 1. 14 choose 14 is 1. That's the case where they all have their exact same GIF, and we want to subtract that out. So there it is. Now all we do is we just take this 14 factorial and subtract that from all of this. And that would be the answer. A student ID is made up of 3 uppercase letters followed by 2 digits. How many possible IDs exist? So you have 3 uppercase letters and 2 digits. So what we have here is we have this one count we're going to get and this second count we're going to get, and we're going to apply the product rule between them. It's like we've got these two, when it comes to an event diagram, we've got this event 1 and event 2, but there's no overlapping outcomes, right? You can't, there's no 2 digits that overlap with 3 letters, but they're connected. We're going to apply the AND criteria between them. We want to, for every unique outcome from event 1, we want to cycle that through all the unique outcomes from event 2. Right? Count that together as different combinations. So, okay. But if we come back here, though, with these event diagrams, you can sort of treat this like it's its own counting problem. If it's a big enough undertaking to get the count for event 1, you have to go to your own separate page of your notebook, right? But it's not that big of a deal here, but I just want to point that out because what I mean by that is here we've got a, let's see, like this could be a combinations with repetition problem, and this could be a permutation problem. We don't know. So, okay, what we've got here on the left, though, is, let's see, 3 uppercase letters followed by 2 digits. This is a permutation with repetition problem. We could choose from a group of 26 with repetition because we could choose 3 A's, etc. So that's 26 times 26 times 26. Now, over here, we're choosing from a totally different group. It's a different event. We're choosing from this other group of 2 digits. So there's 9 outcomes here with repetition. So it's 9 times, or no, it's 10 outcomes. So 10 times 10. And now we just multiply these. So it's 26 cubed times 10 cubed. Okay, now if duplicate letters or numbers aren't allowed, then what you've got is it just turns into, this is 26p3, because now you're picking, there's no repetition. And here this is 10 still p, 10p2. Because order matters. If it's 1, then 3, then you want to count if it's 3, then 1. And same with the letters. So we use permutations. Okay, how many IDs are possible with an even number of A's? Okay, an even number of A's. Well, we can start with this event's just going to be 10 times 10 over here. This has nothing to do with the A's, and they're not telling us that we can't repeat digits or whatnot. Okay, now over here, we just need to break this down into just different OR pieces. So okay, we could have, I guess they're considering 0 A's to be an even number. So, okay, let's start with, what if there's no A's? Okay, well then that's just going to be, that's permutations with repetition, but now you have 25 letters to choose from. So that's 25 cubed. Okay, now what if there's 2 A's? Well, then we've got, so we can choose from, there's 25 letters to choose from for one of the slots, right? Like we could put a C here and the A's here. But then what about the rearrangements? So we need to multiply this by, it's going to be 3 factorial over 2 factorial. The total number of ways we can arrange these 3 letters. And so that is, if you add these, you get the number of outcomes for event 1. So 25 cubed plus, let's see, 3, this is, so 25 times 3 times 2 over 2, so 25 times 3, so plus 75, and then times 10 squared.